let's finish our discussion about the head loss and how we're putting it together. So in the last videos we put together, we've come up with this form that we can find HF and tie it to the shear stress of the wall, and so twice the shear stress of the wall divided by the specific weight of the fluid times the ratio of the length to the pipe radius is going to equal what the head loss for the pipe is. A particular note, I do want you to take a look at something and notice that this has absolutely nothing to do with how the pipe is tilted. It doesn't end up in our final formula here. So just keep that in mind. That's why it's not too terribly important for what we're doing. So how are we going to use this? You're sitting there probably thinking, wait, you just told me that we can't really measure shear stress of the wall, so how is this useful? So we're going to go to a German professor, Julius Weisbach, in 1850. He discovered for turbulent flow that he could calculate out H sub F. Now, I say Weisbach is the one that formulated this equation, but I just want to point out Weisbach built it off the work of Prony, who originally put together an equation, and then came along Henry Darcy. And so more technically, even though a lot of times it'll be referred to as the Weisbach equation, the technical name would be the Darcy-Weisbach equation, which is why Darcy's name is actually in the formula that we're about to write out. So he found that HF would still be the length over the diameter, and then the v squared over 2g, so we're looking at the velocity of the fluid, but we have this constant in here, that's script F. And so what is script F? And we call this the Darcy friction factor. And this is where Mr. Darcy, or Dr. Darcy, comes into the equation. So the Darcy friction factor. So first of all, the Weisbach-Darcy equation, put like 3 or 4 boxes around it. We're going to be solving this equation a lot in this class. You may be sick of it by the end, but we're going to solve this equation a lot. So what the Darcy friction factor is a way to encapsulate and figure out how that shear stress is going to affect the equation. So the Darcy friction factor is a function of a couple of different things. First, it's a function of the Reynolds number based on diameter. Because it's a fluids equation, obviously Reynolds has to be involved in some way. We also have another dimensionless parameter called epsilon over d. So this is lowercase epsilon, because we got to have more Greek letters. So epsilon is going to be our surface roughness. And this is usually a tabulated property that we can look up. We'll talk more about that, about surface roughness a little bit later once we get into charts and everything. But the surface roughness, if I'm looking at the microscopic pipe, and if this dotted line here is the average diameter of the pipe, what epsilon is the average deviation from that main pipe. Whether it's, let me draw this a little bit more in the, so here's my pipe. I wanted to draw it a little bit more in the center because I wanted to show that it can be an increase or a decrease in the pipe. And so it's really a measure of the roughness of the pipe. So epsilon d gives kind of this how rough the pipe is ratio, but also duct shape, because a rectangular pipe will work a lot differently than a round pipe. Just as an aside, Darcy was, he designed a lot of the aqueducts and everything in France. He was the head of the military corps for a while. And so Darcy was from around 1803 to 1858. So he is very known for hydraulics that he did while he was working in France. And so we're going to be playing with the Darcy friction factor a lot and calculating it out. So if we wanted to look at it, so what is the friction factor? Looking at that equation that we put together, we can see that the friction factor we can calculate out is 8 times the shear stress of the wall times rho v squared. Once again, we get into that problem, though, that we can't really measure the shear stress of the wall, and that's why we're going to be doing other things with that.